You do what you do because you see it so clearly, the whole of their budding potential. You do it for that spark, that moment they get it, eyes wide, lit from within. Because when they get it, they positively glow. You do it because to be able to give them that moment, it's beyond a responsibility. It's an honor. It's what fuels you. You want them to look at the world around them with endless curiosity, to nurture their amazement, to fill them with wonder. You want to open them up to infinite possibility, to know that for them, not even the stars are the limit. You do it because you want to give them the universe.
Hi everyone, welcome to UTA Planetarium's another live star stream. First, if you see any links on the comments chat, please do not click on them because previously we had some spammers posting some fake live star streams that ask login information and credit card numbers. Our stream is login free, and absolutely we don't need any credit card numbers to watch this stream. So please do not click on any links. Today we have a special topic, amazing topic. We'll talk about black holes. But I would like to mention about just the summer solstice past Saturday. It was the longest daytime of the year. So that was on Saturday, June 20th, and the summer has officially started, even though the weather outside today is not great. Anyway, I would like to introduce, as I promised last week, I said I was going to bring a special scientist guest to this live star stream, and here Dr. Ramon Lopez of physics department with us today as a special guest. So if you have any questions during the live stream, you can post those questions in the comments chat section, and we will try to answer it as much as we can. Dr. Ramon Lopez is the professor of UTA physics department. He has a PhD degree in space physics from Rice University. He leads a research group that works in both space physics and science education. He has many other duties. He's a co-director of UT Arlington's UTeach program, and co-author and co-author over 120 peer-reviewed publications. He has a lot of awards, and even the science book, Storms from the Sun, and he is absolutely serving on several nationally recognized committees. And welcome, Dr. Lopez.
Hi, Levent. Thanks for the introduction. It's great to be here.
Again, to our audience, if you have any questions during the stream, please post those questions in the comments chat. So I made a brief introduction to what is a black hole in the last week's stream, because we talked about stars' lives. So if I need to wrap up a little bit, so the idea of a black hole has been around actually from 1700s. But the modern story of black holes started with the Einstein's revolutionary theory of gravity that was completed in 1917. So in principle, according to this theory, even a rock, if we squeeze it hard enough, can form a black hole, because under these conditions, the object collapses under its own gravity force and then goes to a zero size. This is actually where the challenge starts, to think, how come a matter can go to a zero size? But according to Einstein theory, the matter can go to zero size, but its mass and gravity remains behind. That forms the black hole itself. But in nature, the rocks don't form black holes, but the massive stars does. And if star is 3 or 4 more massive than the sun, which can be actually the millions of times massive than the sun, those stars form black hole at the end of their star lives. So let me start asking my questions to you. As the object goes to a zero size to form a black hole, in this case, where does that star stuff go?
So when you form a black hole, the matter is still there. It gets squeezed down to incredibly high densities and to a point where there's absolutely no force in the universe that we know of that can stop it from collapsing even further. And that's when you get to this singularity, this thing where it's like 1 over 0, everything blows up and the mathematics doesn't work anymore for you right there. But the matter is still there. Black holes have got properties like the amount of matter, the amount of mass, the amount of stuff in it that creates the gravitational field of the black hole, and the rotation, the angular momentum, that's preserved too. Electric charge, total electric charge is going to be preserved as well. But it doesn't go away. It's just not accessible directly to the rest of the universe, because with one strange exception, something that, once matter goes into the black hole, it's there and can't come out. That's the whole definition, is that you are not able to escape the gravitational field at that point. Not even light can escape the gravitational field. The one exception is an idea that Stephen Hawking came up with years ago called Hawking radiation. And in quantum mechanics, when we deal with things at the very tiny level, the world is very different than our normal world. And things can appear out of the vacuum and disappear, as long as they don't violate what's called the Heisenberg uncertainty principle. So, we know that matter is conserved, that energy is conserved. If I have a certain amount of material, that's how much material I've got, and that amount of material is going to be conserved. If I have a certain amount of energy that in a system, unless that energy goes out somehow, stays conserved. So when you get two particles that form out of the vacuum, they normally just come right back together. Particle and an antiparticle, they annihilate and they disappear before the rest of the universe even knows that they're there. But in fact, it's real, because you can include that in calculations. And if you don't include those kinds of terms in calculations, these virtual particle terms, then you don't get the right number that we can actually go out and measure of some real phenomenon. So we know that this happens. But if you have these two particles appear right next to the edge of a black hole, and one of them goes across the edge, it can't come out anymore. Now this other particle, it's got nobody to annihilate with and to disappear back into the vacuum. And all of a sudden it has to be real. Well, it's now a real particle with real mass, real energy. Where did that come from? It had to come from the gravitational field of the black hole. Fields are energy. And that field is created by the mass of the black hole. So when that process happens, the black hole actually loses a tiny bit of mass. Now, for big black holes, this is not an important thing because they're just so massive that the process isn't important. But a very tiny black hole, they can evaporate. And that puts a limit on how small black holes can be before they basically evaporate through this Hawking radiation process. But other than that, when something goes into a black hole, that's it. It's in there. And it just adds to the mass of the black hole. And that matter is still there, and we see its gravitational field.
Even some of the black holes I've seen, they have companion stars around them, and they are constantly stealing flow of matter into the black hole itself.
Yeah, so you've got a nice picture of that right there. Now, this happens with other stars as well. Anytime you've got two stars together, the one that's more massive is going to, try to pull some material off of the smaller one. So this can happen with, a neutron star and a regular star, or two, big stars that are close to each other. But in the case of a black hole, that matter gets pulled into the black hole, and as it pulls in, it spirals around in that disk. That's that blue disk. And as it spirals in, it's generating a lot of friction, and the material is just banging into other particles in that disk as it spins around, gets super hot, and it glows. And as it falls in, as I said, black holes retain the physical properties of the material that went into them, like the angular momentum and the magnetic field. And that magnetic field is pretty much like the field of a bar magnet. And so high energy particles that are accelerated by all of this liberation of energy as the mass spirals in to the black hole, they get shot out along the magnetic field. And that's that kind of a beam that you see going in each direction. But then the material goes into the black hole, and it just adds to the mass of the black hole, and it adds to the angular momentum of the black hole, and any magnetic field that it carries in adds to the magnetic field of the black hole. So, that stuff is still there. It's just not really accessible to the rest of the universe.
Yeah, speaking of the matters in the black hole, we have a question from one of our audience asking, what is black hole made of? So there are like stars, iron cores, and also the stolen material from around, but they are not in the form of any elements anymore, right? So is there any name of that material?
No, everything is crushed together. Like in a neutron star, which will happen before it gets to the black hole stage. A neutron star is very, very dense, and its gravity is pulling down on everything, and it in fact crushes the electrons and the protons together, and so it's basically like one big nucleus of neutrons. And if it's massive enough, then not even the pressure of the neutrons pushing on each other can hold back the further collapse, and that's when you get to the black hole stage. But it's not like any matter that anybody here would ever have an encounter. And you wouldn't want to encounter it either, because it would be pretty deadly if you did. I mean, even neutron star material, if you take, a tablespoon of a neutron star, that's got the mass of Mount Everest. So you wouldn't want to be anywhere near that.
And because of their huge gravity, they also affect space and time. So how does it work?
That's where Einstein's theory of general relativity comes into play. You mentioned that the idea of something that we could call a black hole goes back a long time. That's because in Newton's gravity, light can be bent by gravity. A lot of people don't realize this. They think it was just Einstein who said that. No, that's not correct, because in Newton's theory of gravity, say everything on Earth falls at the same rate, and the mass of the object doesn't matter. So if I drop, like Galileo, going to the top of the Tower of Pisa, dropping the heavy ball and the light ball, and they both hit the ground at the same time. Or you can Google and find on YouTube a scene where in a vacuum chamber, this huge vacuum chamber run by NASA, a hammer and a feather are dropped. And without the air resistance, they both fall at the same time and hit the ground at exactly the same time. So it's pretty neat to see. So in Newton's gravity, everything falls at the same rate, and it doesn't matter what the mass is. And Newton thought that light was made up of little particles. He wasn't thinking about photons the way we think about them in modern times, but in Newton's picture, gravity would attract light even though it had zero mass, because gravity, everything falls at the same rate in gravity, in Newton's theory. The thing about Einstein is that he completely changed how we think about gravity. Gravity is not a force anymore. Gravity is a property of space-time. And matter bends space-time, and then things move in straight lines through curved space-time. So if I'm sitting here and I see an object that's moving, and the object is moving straight on a curved surface, I see the object actually moving in a curve. And so I would say, oh, there's a force on that object that's making it go in a curve. But in Einstein's gravity, it's just space-time is bent by gravity. And that's Einstein's field equation. On one side, you've got the mass of whatever is making the gravity. And then there's an equal sign. And on the other side, you've got the shape of space-time. And that's what all matter does, is it warps space-time. So around every person who's watching this, there's a little warp in space-time because of their mass. And around the Earth, there's a warp in space-time because of the mass of the Earth. And when you start getting to large objects like stars, then you can get really big amounts of warping. And especially when you get something that is so dense like, you know, neutron stars, or then the extreme of the black holes. But this is happening all around us. You know, I think everybody's got one of these, cell phone. And one of the most important things I remember when I got my first cell phone, the first smartphone, was that it had GPS on it. And I could actually navigate with my phone. That was just like absolutely amazing. Well, how does GPS work? You have a bunch of satellites in orbit around the Earth that are sending radio signals, and then the receiver looks at the different signals and then figures out where it is. But to do the calculation correctly, you have to account for the change in space-time produced by the Earth. Even for just GPS, you have to include Einstein's calculations to get the right answer. So the black hole is the extreme case, but anywhere where there's mass or energy, space-time is bent by the presence of that mass and energy, and it is just the amount of mass gives you the amount of bend. So Earth is only a planet, we don't notice it, right, in our daily life. But when we build a technology like GPS, we notice it, because if we don't include that part of the calculation, we get the wrong answer.
So what happens to time around black holes, or in the black holes?
Well, you and I are experiencing time at basically the same rate. If we were to start clocks and stop them, they would show basically the same time. But if I were in a very strong gravitational field, my clock would run slower than your clock. And eventually, if I get to infinite gravitational field, you know, at the center of the black hole, then my clock stops completely. If I cross over the event horizon of a black hole, so that now actually I can't get out, if it's a really big black hole, I might actually not notice it right away. I just wouldn't be able to get out. But as I go deeper and deeper into the black hole, my clock would start to run slower compared to someone on the outside. I wouldn't notice any difference. I would just sit there and, you know, I could watch an episode of The Simpsons and it would still take half an hour in my local time. But somebody outside would see that it took a lot longer because my clock is running slow. So that's one of the reasons why you have to include general relativity calculations for GPS, because on the Earth, we're deeper in the gravity well. We've got stronger gravity here on Earth. In orbit, the gravity is almost the same, but you're a bit further away. So it's a bit different. It's a bit smaller. And so the clocks run at different rates. And you have to include that in the calculation so that you can really triangulate the radio signals and know just where you are on the surface of the Earth. So
I think
clocks run slower in high gravity.
Yeah, that brings us to the astronaut analogy. An astronaut is having a twin sister or brother and then going into space. And because he or she is further away from the sibling on Earth, they are aging at different rate, right?
Their clocks run at different rates. Now it's tiny. It's tiny. So on our scale, we wouldn't really notice it. If you're here on Earth, we're pretty close to sea level here in Dallas-Fort Worth. But if I talk to a friend of mine, say in Boulder, Colorado, that's up at 6,000 feet, they're higher up. And gravity is a tiny, tiny bit weaker there than it is here. Not enough to notice anything, but their clocks are running a little bit faster than my clock. But I would have to run that clock a really long time to see any real difference. Mm-hmm. Because on our time scales, it doesn't matter if there's a billionth or a 10 billionth of a second difference between two clocks. But when you talk about how far light travels, those kind of small times can lead to large distances. And that's why you have to include those calculations, those corrections, to get GPS, because it's using radio signals that travel at the speed of light. But I'm never going to notice a difference in my personal clock if I go, say, up into the mountains and spend a year there and come back down. Although I could do the calculation and figure out what was, how much extra time I got out of it.
That's great. Question from the audience. Can black holes die?
Can they die?
Can they die?
Well, it depends by what you mean by die. By die, you mean it disappears. So if it's a tiny, tiny black hole, then in principle, it can evaporate through this Hawking radiation that I mentioned earlier. Other than that, the black hole is going to be there for a very, very, very long time.
How about the wormholes? The speculative black hole tunnel that we can imagine or we can visualize as it is allowing or connecting two faraway points of the universe and making a shortcut in them. Do they exist?
There's no evidence that they exist. I mean, there are some theoretical arguments about whether they could exist or not. But other than at Deep Space Nine, so that there's the wormhole there that the Dominion came through to attack the Federation, I don't know of any wormholes.
Question from the audience. Dr. Lopez, are you an instructor for any courses at UTA?
Yes, I do teach classes at UTA.
And I did take a general relativity class or classical mechanics graduate class from him. He's a great instructor. So let's continue with our questions. And I have a question. Could time go backwards in space?
We have no evidence that ever happens, and we have no theoretical framework to say that it can happen. But remember that we still don't understand a lot about time and about space. And Einstein's theory of general relativity is a very powerful theory, but there are times and places where it breaks down, and it just doesn't allow us to understand what might be happening. So is it possible that time could run backwards? Maybe. No scientist is willing to say that absolutely something is 100% impossible. It might be 99.999 and then a billion nines after that percent impossible. But 100%, that's a difficult statement to make, because you can only make that statement when you understand everything, and we're far from that.
Question from the audience. How close is the nearest black hole to Earth?
It's about 1,000 light years away. And that's the kind of question you can Google very easily. So, if we don't have time to answer all of the questions today, for those of you who still have questions, just take the question as you typed it and put it into Google and see what Google gives you.
Sure. Another question from the audience. Can Hawking radiation be harmful? Is there any known history event caused due to this radiation?
No, and in fact, we've never really observed it directly, so we can't it's theoretically possible and on fairly solid theoretical grounds that you would expect that it could exist, but I don't know of anybody who, well, we've never been up close to a black hole, so we can't really, say that we've measured something like that because we haven't been next to a black hole. And to be honest, there are certain things that I would like never to directly encounter. Black holes is one. Tornadoes is another thing. You don't want to be close to a tornado. It's an interesting thing to study, but you don't want to be close to a tornado.
Yeah, that's a great analogy. This brings up to my another question from my notes. Are there any threats to us from black holes?
If a black hole, if there was a supermassive star nearby that could at some point become a black hole, that would be potentially a major catastrophe for Earth, not just from the black hole, but the actual collapse of the star and the huge interstellar shock wave and radiation that would produce. But we don't have any stars nearby that have those characteristics that could cause an extinction level event here on Earth. Now, back in I think it was 1908, I'd have to look it up to see for sure, but 1908 there was an explosion in Siberia that's called the Tunguska event. And for a long time, it was thought that maybe it was a comet or an asteroid that hit the Earth. But the problem was that there was no crater and no material like if an asteroid had hit. But trees were flattened for hundreds, thousands of square miles, just flattened by this enormous explosion. And one of the ideas that has been suggested that I don't think really you'll get many people defending this idea, but one of them was that actually a tiny black hole actually hit the Earth and that caused this event. Problem is it would have gone through and then there was no thing on the other side. And actually the most recent idea is that the reason we don't have a crater is because a big asteroid came and just grazed the planet. So it came through the atmosphere, blasted out a shockwave that flattened all the trees, created this explosion, but it bounced off the atmosphere and went out.
That's very interesting. Question from the audience, can a black hole spin backwards?
Well, what's backwards? I mean, if I take a ball and I start spinning it, is it spinning frontwards or backwards? I can specify clockwise and counterclockwise depending on where I want to look. So a black hole can spin any direction it wants to.
And how many black holes are we currently aware of?
Oh, I have no idea. But we believe that every spiral galaxy like ours has got a supermassive black hole at the center. But then there are others. I mean, I don't really know how many people estimate that there are in our galaxy. But that would be an excellent question for Google.
Now, my last question is are Einstein's theories still good to study the black holes? And what are we trying to learn out of black holes by studying them?
Oh, yeah. Einstein's theory is still absolutely excellent. And there's a detector called LIGO, which measures gravitational waves. And it's not the only one. There are others now that are coming online. But LIGO, some years back, got the first evidence of gravitational waves that were predicted by general relativity. And it's another way that we can learn what's happening in the universe. So we can look at these gravitational waves and we can combine that with information from other telescopes to get a fuller understanding of events that are happening in the universe and to test our ideas of how we think the universe works. So Einstein's theory of relativity is still, is absolutely the way that we understand the large-scale structure and evolution of the universe. Now, I should say, that although Einstein's theory, in a sense, replaced Newton's theory of gravity, if you want to do a calculation of spacecraft trajectories, you use Newtonian kind of mechanics. It's just that under certain extreme circumstances, general relativity gives a different answer. than Newtonian mechanics, and under those circumstances, you want to use general relativity. But you know, Newton's F equals ma is still as applicable today as it was when he first wrote it down. And in the same way, even if we, at some point, we'll go beyond what Einstein did. And we'll have a new theory. And maybe it'll be one that combines general relativity with quantum mechanics, because we don't have a theory for that right now. But at some point, there'll be a new genius who will do a new synthesis. But that doesn't mean that Einstein's theory will be wrong. It will be just that it will have reached its limitations. Just like Newton's mechanics, it's not wrong. It just has limits. It doesn't work under certain circumstances because it doesn't take into account things like space-time, both special and general relativity. And that's what Einstein added to the whole picture.
Well, I know you have another meeting that you need to attend, Dr. Lopez. I would like to thank you very much for attending our live star stream. And here today is, we talked about black holes, and next week we are going to be with you again with another exciting subject. In the meantime, you can keep posting your questions to the comments chat, and we'll go ahead and answer them later today. I hope you have a great rest of the week. Yes.
Thanks very much. It was a lot of fun joining.
Yes, it was a great pleasure to having you, Dr. Lopez. All right, everyone, bye-bye.